Almost there, folks. Well, we made it. Looks like we can get started. Welcome back, everyone. So this week is going to be a little bit unusual, like we mentioned before. I have a schedule conflict that affects Thursday's class. So on Thursday, we won't have our normal class, but I still will hold office hours from 4 to 5 o'clock. I'll be in that room 220, just right over there. Also, what we'll be doing on Wednesday, that's just tomorrow, is we'll be reviewing for the very first exam. So the sample exam is posted here. The lecture notes here are all blanked out. They also qualify for a great way to study for the exam, but they're the same old problems we've seen before. If you want fresh problems, you can find them on this document here. Another thing that bears repeating on the exam is it will use the TIE4 calculator for one of its problems at least, and that's going to be calculating the sample mean and the sample standard deviation. So if you're pretty good on working on those procedures, then I'd say practice it a few more times and you'll be in really great shape. The exam only goes through section 3.3 and double checking. That's the one that involves things like interquartile range and median. So I guess we'd have to know how to do that as well. But if you can get your sample mean and sample standard deviation, then it's just going to be different output in your calculator that you'd have to dig out. So what we'll also be doing on Wednesday, I'll post another quiz, same kind of deal like we did before. I'll be due on Monday, but this quiz is kind of special. It's going to be a quiz that's based off any one of these sections right here, but it's going to be kind of review in a certain sense. I mean, if you do a box plot, you have to first come up with lower quartile, upper quartile, and the median, same kind of stuff in section 3.3, and then you just sketch the plot. So if you get through that quiz on its own, that's going to be a great way to study for our upcoming exam on Monday. Well, that's my full spiel for the announcements. Any questions at all, folks, before we get started? Okay, well, we're nearly done with getting through box plots on this section here. We're only going to start section 3.5, and we'll have to put it up on the shelf for a little bit after we finish off our exam one. We'll return to it after Monday, September 18th. So let's get started then on section 3.4. This is pretty much where we left off, determining if we have a box plot, what the symmetry situation might look like, whether it's highly, roughly, symmetric, or clearly skewed in a particular direction. And I believe we did take a look at those matters a little bit before. It would have been in section 3.3. And this is the idea we were dealing with. We said when we first took a look at these statistics, medians and quartiles, if the median is closer to the first quartile, Q1, than it is to the third quartile, Q3, and we mean substantially closer, like in this scenario, then we have evidence that the data is skewed to the right, even if we don't even look at a histogram or even a dot plot. On this one, we did look at a dot plot and we very well confirmed the skewing. If the situation is different, if the median is closer to, say, the third quartile, then we're going to have skewing to the left instead. So that's the kind of idea that targets what we're about to build on these displays here. Well, first, let's try for high symmetry. What I'm going to do is put down a box plot like the ones we've seen right around here, but I'm going to focus just on the box part, less about the scale. So something that's highly symmetric ought to look about like this. The inner box could be narrow, it could be pretty wide, but if you have highly symmetric data, then keep in mind, right on this value is the lower quartile, right on this value is the upper quartile, and the median should be right about in the middle. Maybe not perfect, like this one is slightly edging off towards the right, but I would consider that as it stands, we're looking at highly symmetric data. Then the whiskers should be pretty balanced as well. And that's what it ought to look like. So if you're looking at multiple box plots all at once, this is about what you'd be seeing. Now let's start making it a little bit worse. First, with rough symmetry, all I have to do is move this bar closer to either quartile 3, like in this case, or to quartile 1 over here. So if something is roughly symmetric, it could look a bit more like this. So I'm going to make it go, this time much closer to quartile 1. We can put a whisker going off in this direction, whisker going off in this direction. And although it's definitely not centered for the median bar, it should be closer to where the red dot is, we still have pretty good symmetry in this. Again, this is kind of tough if we're just looking at a box plot and we don't see a histogram. The histogram is better to determine symmetry versus skewing, but this is all about, you can still get some information if you're just looking at the box plot. Well, the next two are going to be a little bit funner, skew to the left clearly and skew to the right clearly. But any questions first with those two displays? Okay, let me add here, just as a reminder, we usually don't add these to box plots, but in orange, this would always be the minimum value. This would always be the lower quartile, Q1. This is the median. This is quartile 3. And this would be the maximum value. If we had a scale, we would just look down and find those values. Well, now let's take a look at clearly skew to the left. And this is tricky. It's not hard to make it clearly skewed. If you want to make it clearly skewed in a particular direction, to me, that is a little bit tricky. So I'll leave it up to the class. If we want it skewed to the left, should the median bar be closer to this edge or to the other edge on the right? So I'm saying to the left edge here, or to the right. Oh, I got to think in the right terms. I agree, it ought to be around this edge. If we put the median somewhere off right here, then another reminder about these box plots is from here to here, that's 50% of the data. That's the inner 50%. And that means from, this is almost kind of hard to indicate, from here to here, let me zoom in on that. That's 25% of the observations. And from here to here, all the way out there is the other 25% of the central 50%. The median cuts everything in half. And so already we have a high concentration on the right and things way more spread out on the left. And we haven't even added the whiskers yet on the plot. So if your median looks like this, we have quite a lot of skew that we're dealing with. Let's finish out putting the whiskers on this. From here to here, that'll be the extent of the data going to the right. And going to the left, it could look about like this, and we might even have several outliers that are beyond that location. So this value would be the max. All three of these are outliers. And this is the location of the largest value that is not considered an outlier by the 1.5 IQR rule of thumb. Let's add those notes right here, since that's a lot of information already. So this value would be the max. Oh, sorry, that would be the minimum for thinking left for smallest. Thanks for fixing that. That would be the minimum. This one would have been the max. Well, let me spell min right. That's an N there. This one's the max value since there's no outliers to the right. Here we do have 3 outliers. Again, this is by the 1.5 IQR rule of thumb. And that value is not the minimum. It's going to be the smallest value after taking out the outliers. So if you wipe out the outliers, you plot them like this. This is just the smallest value after those 3. Well, does that make sense to folks so far? Okay, thanks for the spotting. That was not the max. The left ought to be considered minimum. If we go horizontally, if they were aligned vertically, the bottom would be the minimum and the top would be maximum. So that's the big takeaway on this. The median bar is closer to your upper quartile. Your data is way spread out here, causing our left skew. That means the one down below is a little bit faster. We just need to make a box. Sometimes they can look a little strange. The box doesn't have to be that wide. It could be narrow. And sometimes you might see this even on a WebAssign problem. I'm going to put the median bar right here. And the way it'll be indicated that there's an overlap with Q1 and the median bar is it'll just be really bold right there to say it's conveying 2 statistics in that location. It could have a whisker, potentially, but some box plots might not even have a whisker. It's possible that quartile 1 is equal to the median, which is also equal to the minimum. your data could have looked like this, for example, 3, 3, 3, 3, loads of different threes, and then the data finally starts giving you maybe 7s, 8s, 12s before it ends. If you have a lot of repeats and they're all minimums, that could be what your block spot looks like on the left. It looks damaged, but that's because the minimum, the lower quartile, and the median could potentially be all in one spot. Then we could have it go off to this location. And because we have 50% of the data going off to the right, we have right skew here. Let me add a little bit more. On this box plot, the minimum is equal to the lower quartile, Q1, which is equal to the median value M. That'd be weird data with loads of repeats like I'm indicating here, but it's plausible that you could run into one of those. Doesn't mean the display is damaged. This means slightly weird looking data and absolutely right skewed this time. Well, that's finally our rundown of box plots. Any questions or comments at the moment, folks? Okay, I do have one thing that we could throw in here if folks are curious. One question that's really common after you do all this is, why do we care about box plots? I mean, it's an honest and a good question. We can already do a dot plot really fast, and that tells us skew left or the right. It can show outliers and show where the center is. Plus, we can just produce a histogram with computers, and that's even better. So the reason why we like box plots is more for this reason we're about to show. I'm going to go to a different class just for a moment and pull in a separate display that shows loads of box plots. Let me see if I can do this in a quick way. So just a small mental break for us. This would have been, I think, in chapter 2. Same kind of stuff that we did essentially. Oh dear, is it actually here? Sorry, let me try again. Not chapter 2. Maybe it was chapter 1. Here, I seem to have lost that graphic. But let me try one last thing. Side by side, box plot displays. Let's just go to images. This is always my go-to if I can't find a file I'm trying to find. And this is how you're usually going to see box plots. This one looks like a pretty good one. They're doing them horizontally like we're doing. And usually it's easier to open an image. There we go. One more click, finally. So oftentimes a single box plot is really rare. If you put all your data into one box plot, I mean, that's not terrible, but that's not the best use of box plots. It's really something like this, where you'd really absolutely want a box plot. Let me put this on our current notes. What's special about this display here is, sure, we have numerical data. I'm not sure what the scale represents. If it's response, maybe this is, say, like calories burned or something like that. Then we have 4 different groups. And so you typically want a box plot if there are 2 variables in your data. One of them is numeric, and another one is categorical. The box plot splits the categories and lets you compare amongst all these different groups. There could be dozens of different box plots. Here, between the 4, we can see that for 1, 2, cell 1, cell 2, whatever those mean, the center on this one is right about here. But for the second group, it moved to the right a good bit. So there's actual separation in this data. Here it moved to the left, but between these 2 groups, there's a lot of overlap. So box plots are usually used in this kind of scenario where we're comparing multiple groups all at once. Sadly, we can't get into that too far since it's only an introductory class. We pretty much just build a box plot and stop. But it's good to know they have more value aside from the one display there. Well, I think we did it, folks. That's the conclusion of getting through box plots. Any questions or comments at all at the moment? Okay, well, this takes us finally to the last section of chapter 3. Again, this won't be on the exam. but certain parts of it are actually pretty good review for what will be on the exam, and I'll try to mention it as we go through those portions. Let me just close these million different tabs I opened. Okay, so back to section 3.5, but before we do, I want to point you to something that is a little bit weird about our statistics at the moment. We just got through section 3. Oh, geez. I need to get to the right class. Sorry, I should have moved Moodle classes mid-class. That's a bad experience for me. It can't be great for you folks. Sorry about that. So now we're back to section 3.3. Let me show you what's weird about these statistics compared to 3.2. In 3.3, it's not hard to say what the median represents. It's just the 50th percentile. Literally, it cuts the data in half. 50% is lower than the median, 50% is greater. Interquartile range is a little bit more tricky, but it still tells us how the data is spread out and in what way. If we go to, say, this right here, that length is the interquartile range, and it tells us, for looking at just the middle section of all the data, how wide they are spread out. So it gives us a feel for how spread out all of the data is just by that number. But don't forget, we also calculated these statistics. The sample mean is the arithmetic average. It does follow the skew, but when things are symmetric, it's very close to the median. It does a great job of telling us what the center is. And the way we measure variability is through the standard deviation. But my question now is, here's the weird part. In what way does the standard deviation tell us how spread out the data is? Well, larger standard deviations means more spread out, and smaller, closer to 0, means less spread out. But we don't have yet an analogy that's like this, the length of the central 50%. So that's what our next section is all about. Just how does the standard deviation tell you how spread out the data is? That's really our major goal now in this last section. So when we turn to these notes, let me first give you a preview of what we're going through, and then we'll start off. The z-score is going to count how many standard deviations an observation is away from its mean. So the z-score is already going to be a hint on how the data spreads based off its standard deviation. Then the big punchline is really this graph right here. This is called the empirical rule, or the 68, 95, 99.7 rule. And essentially what it's telling us is, if we take some sample data, then whatever our mean is, we expect, let's take a look, 68 observations to be within one standard deviation going to the left and one standard deviation going to the right of the mean of our data. So it's in that way the standard deviation is telling us about where all of our data is. So interquartile range gives you the central 50%, and this rule will give you the central 68%. But it comes with conditions. Your data has to be mound-shaped, like what we see right here, and it also has to be approximately symmetric. The moment it becomes highly skewed, well, the standard deviation does not follow by these rules any longer. So we'll be practicing with the empirical rule through this display. We'll check out a couple problems, but it first all starts with z-score. So that's going to be our goal today. We'll probably get mostly through the z-score and end on the normal curve that we saw there, the empirical rule, coming back to it after the exam. But any questions at the moment, folks, before we start? Okay, let's begin with dissecting this definition. And there's a lot going on with this definition. Some of the questions that you'll see in WebAssign are really just based off these kinds of statements that you see down below. So for the purposes of homework, it's a really good idea to come back to this original definition. I'll put this in purple. This is the main entrant of these notes. The z-score has to deal with a particular data value. And when they say a particular data value, we're talking about X in the formula. So whatever the data value is in question, we can calculate a z-score based off of it. The way we do it is we subtract the mean, written as X bar or just the mean in ordinary words. And then we divide by the standard deviation, S. So that's going to be our z-score formula. The overlap for purpose of reviewing for exam 1 is calculating the X bar and the S. That's definitely on exam 1. So what does the z-score do? Well, it could be either positive or negative. If it comes out as positive, then your data value in question is going to be to the right of the mean. If it's negative, the data value is going to be to the left of the mean. And if we look at the formula here, because you're dividing by S, the unit of this is number of standard deviations. So Z is number of standard deviations that X is away from X bar, its mean. So that's the breakdown of the formula, and we'll spend a good amount of time just practicing it. But first, any questions or comments so far? Okay, so that's how it goes. There's a lot of stuff here that looks like fluff, but the author of our text, who also has questions the web assigned for us, built questions based off this information here. So I'll take a screenshot here. I'll just kind of tuck it away down there so it's always visible. And now let's give a try on this problem here. It's not the most exciting problem. It's about light bulbs and watching them burn out, but it's important work. And it says here, a sample of 6 light bulbs were selected from a production line, and their lifetimes were measured in hours. The data are as follows. Why would you ever want to do that? Well, if you're going to produce light bulbs, you have to have an expected runtime, the average amount of time the light bulb will run. And so it looks like that's what they're trying to do. Validate if the production run for the light bulbs is really up to spec. First thing we see here is it said 6 light bulbs. Also, we have 6 observations, so n equals 6. And part A says, use a calculator or computer. It won't say or computer on the exam since we'll just have the calculator to find the sample mean and the sample standard deviation of these observations. That will go for 2 decimal places to round. So that's our goal. And again, this is the review part for exam 1. Let's throw all this into the calculator and see what we get out. First things, hit the on button, stat key, and enter right away. Then if you have loads of data, up arrow and clear, then enter always saves you loads and loads of time. Last thing to do is just dump in these 6 different values in, being extra careful. So 986. Oh, and I already made a mistake. 968. That's very important to get that right. 893. 769. 845. 922. And 915. Okay, we've got 6 observations imported into the calculator. So next keys, hit stat, right arrow, and a bunch of enters. I'll pause right here on this screen. Okay, now that folks have had some time to throw that in there, just to check with the class, are those numbers looking okay with folks? Okay, awesome, glad to hear that. So if you're getting your X bar here and your SX right here, then you're in great shape for operating a calculator for the purposes of exam 1. I did mention you might have to calculate quartile 1, quartile 3 in the median, but you would just hit the down arrow key to pull up those values here. Let's go back up to the top. I'm not super concerned about rounding. So as long as you've got the right information here, if you gave me 885.32, then I'm going to give you full credit on that for an exam, certainly. But it's always good to be careful. It's mostly practice for WebAssign, really. The sample mean comes in as 885.33, coming from that first value there. And last, the sample standard deviation is SX. This one will be 69.68. And I put the X in, just, I guess I'm really good at copying, but ordinarily we would just write S. It's okay if you do put the X there. S equals 69.68. Well, we did it, folks. That's the first step down. Now, here's the new portion of the notes. I wouldn't ask part B. That's going to be on exam 2. We're being asked, what is the lifetime of a light bulb that is 1.5 standard deviations above the mean? And I mean, that's a confusing question when you look at it at face value, right? It's essentially just a word problem in math. But what we want to tie together is, let's see, this portion right here. So the z-score always tells you how many standard deviations the data value is away from the mean. We're going to be 1.5 standard deviations above the mean. Well, we really just have to go like this. Let's take 1.5 standard deviations. Right here where it said above, we're going to use a plus. Oh, and I forget one thing. Let me back up to this portion. It says 1.5 standard deviations, so we'll go to here. Right where it mentions standard deviations, just insert S. So with what I've written so far, there it is, 1.5 standard deviations. If it says above the mean, now here's where it's a good time to put in the plus. Plus will go to plus only because it said above. If it said below, we would calculate a minus. Then when it says the mean, well, we have that value too. That's just referring to X bar. And so that's all we have to calculate on this one so far. Does that make sense to folks at this stage? Okay, so all we need to do is, it's kind of like calculating interquartile range. It becomes a math problem where we do a couple substitutions. First 1.5 goes in. Coming from here, we look up S, 69.68. I'll indicate multiplication with parentheses, and right this way. 69.68. Then plus to plus. And X bar is the 885.33. So now all that's left to do is just jam this into the calculator and we'll be in great shape. And it's definitely kind of a weird problem. All we really did was read it left to right, dump it in, and now we calculate. So we'll go 1.5 times 69.68 plus the mean of 885.33. So that's our value we're going to get, 989.85. And by the way, there's context to these numbers. These all have units. These were run times in hours. And so this would be in hours as well. So now what part B is saying is, if you have a light bulb that lasted 1.5 standard deviations above the mean, then its runtime would be 989 hours. Well, almost 990 altogether. Looking at these data here, that's the way in which we start to get a feel for what the standard deviation is in a certain sense. If you're already 1.5 standard deviations above a mean, that's well away from actually all of the data we have here. So that's quite far. 2 standard deviations is considered quite far as well. And by the time your 3 standard deviations are even farther, that starts to become outlier territory at that point. So that's one computation down. We didn't use the z-score formula directly, but the purpose of part B and coming up part C is really just to think of what is the standard deviation telling us. Is 1.5 standard deviations a lot? Turns out, yes, it definitely is. And since that was so fun, let's try it again with part C. Let me move the formula around. Part C is asking, what is the lifetime of a light bulb that is 2.8 standard deviations below the mean, round to 1 decimal place? It's kind of a redo, right? But the thing that's new is where they said below. If they say below, in the formula that we write, we have to use a negative sign as opposed to a positive sign. I'm not sure what's wrong with that thing down there. Let's just hide it for the moment. So writing this out, let's see, it says 2.8 standard deviations. So we can begin with just a 2.8. Standard deviation is S. To me, this is the tricky part. Below the mean means subtract. And then the last part is just going to be X bar, the mean. Makes sense so far? Okay, now last thing to do is just plug in our missing information. 2.8 just copies down. S, let's look that up, is 69.68. Then we'll go minus, let me put that in black. X bar we look up, it's 885.33. And now before we calculate this, let's take a look at the original data above. The smallest observation was this light bulb. It only ran for 769 hours. But when we said 1.5 standard deviations above the mean, we got something that exceeded all of the data. It was even larger than 968. So we're going from 1.5 to nearly 3 standard deviations below. We're expecting a value that's much lower than the 769 we see here. This is going to be a very small value. So let's take a look and see just what we get. We'll go 2.8, 69.68, then minus 885.33. So this time, I feel like I have a mistake here. Oh wait, I do have a mistake. Let me try this one more time. I have it right in the calculator, but I did make a mistake on paper. Kind of an embarrassing mistake. Anyone see what their algebraic mistake is on this right here? Yeah, sorry, go ahead. You're on the right track. It's about that negative sign. I should have moved it around in this kind of way. It should have been, I take the mean. So here's our X bar. We need to go below. So below matches up with minus. We go below by that amount, 2.8 times the standard deviation. So 2.8 times S. Definitely a silly algebraic mistake, a very embarrassing one, but those kind of mistakes do happen. We didn't detect it on this one because of the plus. Doesn't matter where you put your X bar if there's a plus there. But the moment you're subtracting things away, X bar ought to come first because we're subtracting 2.8 times S from it. So again, these are kind of tricky problems. It definitely tricked me. Sorry about the confusion on this one. Does it make sense to focus on why it should be in this format instead? Awesome. Let's calculate it from now a better position. We look up X bar. It comes out as 885.33 minus 2.8. And we're going to multiply that by S, 69.68. And let's see what we get this time. Definitely the negative is a really concerning thing to get here because all of our run times are positive and our mean is quite large. We shouldn't have expected a negative at all. So now let's try this out this time. 885.33 minus 2.8 multiplying 69.68. And that's the value I was expecting this time. 690.22 is what we'll round to. Let me double check our rounding on this. Oh, they said 1 decimal place. That kind of makes sense. Our statistics are more accurate, so we can work with them. And then the follow-up computations, we're rounding to 1 place. So this one would be 690.2. In hours. The one above also is supposed to be rounded to 2 decimal places. But you know what? Let's leave this one stand, mainly because I'm not too picky about rounding on quizzes, neither exams. If this was a real exam question where you're meant to round to 1, but you just gave me more accuracy, I mean, I could never complain about that. That would be just fine. But that's what we had here. If we're going below the mean, and we're going about 3 standard deviations nearly, we're expecting something that is well below this value right here. And that's what we got, a very minimal value. So the takeaway here is 1.5 standard deviations is a lot. Once you're getting about 3 standard deviations away from observations, that becomes really, really far from where the mean is itself. Any questions so far, folks, to this stage? Okay, last 2 questions. We're still thinking about standard deviations. We'll still need the statistics X bar and S. And now we're going to need the formula as well. Let's bring that up. So part D says, suppose another randomly selected light bulb is tested, and that one runs for 693 hours. Let's highlight that. The question then is, how many standard deviations away from the mean is this observation? And we'll round to 1 decimal place. Now, if we look up the highlighted text here, the z-score tells you how many standard deviations the data value is away from the mean. So this is really a problem where we're going to calculate z. And here's how you can tell. It's pretty much right here. The takeaway here is the z-score tells you the number of standard deviations away from the mean. So any question that starts like this is automatically a z-score computation. And it's a tricky computation when you do it in WebAssign because that's how they ask the question. You just have to know they're referring to a z-score when a question comes in this kind of way, because the z-score does calculate number of standard deviations. So let's give this a try. It'll be z. I don't know why it's doing that. Let me just move it over here. There we go. Oh, geez, it went down again. We'll just work with that. So I started with z. We'll write a fraction that goes like this. And now we have to pick out some values. The mean is not so bad. We'll look it up like before. There's always going to be a minus. And x bar, the sample mean, always, no matter what, goes into the second position right here, the numerator. It's always the second term. And then no matter what, your standard deviation, S, is always below. But sometimes the value that goes right here, the particular value, can be hard to find in the problem. Anyone spotted what it should be? Definitely kind of tricky. If you're not sure, I understand the feeling. Any random guesses or any favorite numbers you just want to throw out? Yeah, go ahead.
Wouldn't that be the data value?
Sorry, say again.
Wouldn't that be the data value?
You mean the 693?
Yeah.
Yeah, absolutely. So that's pretty much the value that's in question. The data value with a particular value is the 693 that goes right here. It's definitely kind of tricky sometimes. We just have to know that that assembles right into that location. And kind of the takeaway is the X that goes here is the thing you're trying to calculate a z-score for. When they said something ran for 693 hours, and we want to know how many deviations that's away, that's the thing we want to calculate the z-score for. So we just take the 693, throw it right in here, and now we're in business. So next thing to do is just plug in the other missing information. So I'll go 693, a minus. Let me scroll up for a moment. Sample mean was 885.33. I never seem to make these fraction bars long enough. Let's extend that. And the standard deviation is 69.68. So that's our computation there. And even though this is on exam 2, I want to mention this still for exam 1. On any kind of exam where you have a lot of calculations like this, that's eventually going to go into your calculator, it's always a really good idea. Show this on your exam paper too. Tell me what's about to go into your calculator, and you will always get a great deal of partial credit. That way, if I made a simple mistake in the calculator, I'm not going to just take away all the credit. I would circle this and just say, must have been a calculator problem. So let's go and put this in. 693 minus 885.33. The moment we divide by 69.68, the unit of this is standard deviations, 69.68. And the reason for that is the numerator is in hours, the denominator is also in hours, and so everything really cancels, leaving just number of standard deviations. And here we get a negative, but it ought to be. The value in question, the data value 693, is smaller than 885. So we should have it that's to the left of the mean, expecting a negative sign. So to one decimal place, we have negative 2.8 standard deviations. I'll put STD for standard and DEV for deviations. So let's double check. If we said 690.2 is 2.8 standard deviations below the mean, then, well, this one, it was really close. It rounded to 2.8. It was really 2.76 negative. And the runtime 693 to 690 were also very close. So it's like we calculated the z-score on the opposite end of what part C was telling us to do. Any questions, folks, with that one there? Okay, so that's our z-score computation. Let's try this again one more time. This one is a little bit different. I think we probably do want it on a new page. We'll just throw the formula there and give part E a try. This time it tells us the z-score for another randomly selected light bulb is z equals 2.18. So we have that information, and the question says, how many standard deviations away from the mean is this light bulb? So we're on this question right here. And I honestly think that's kind of a strange question. Anyone happen to know what the answer ought to be to that one? Yeah, go ahead.
2.18.
Exactly. It's a weird and awful trick question in a certain sense, right? But always remember the z-score being 2.18. They told you straight out that's the number of z-scores or standard deviations you are away from the mean. Awful web assigned question when it comes out. But we can say here, the observation is, we go back to the z-score they gave us, 2.18 standard deviations. We can just say away from the mean right here if we'd like, but you could be more descriptive. That's a positive quantity, 2.18. So we can say it's 2.18 standard deviations above the mean. If it was a negative 2.18, we would have said below the mean instead. So again, these questions are weird. They're weird also in WebAssign. That's all about the interpretation of the z-score that gets us through a lot of this kind of stuff. Does that make sense to folks on this question here highlighted? Okay, I usually don't do this. This is more than one question rolled into part E. But here's the next question. What was the lifetime of that light bulb? Well, all I know is 2.18 standard deviations below the mean. If we want to know the lifetime of the light bulb, what they're asking for us is, what was that original data value? Let me highlight that in yellow to connect the thoughts. And here's the second part of the work. We can just write if we'd like, because they gave us a z-score. Here's the formula. Z equals, we take x, always subtract the sample mean afterwards, and then divide by the standard deviation s. So when they asked us what was the lifetime of this light bulb, they're asking us to find the value of x right here. So here's another way the z-score formula is absolutely kind of tricky. There's 4 variables wrapped up in that. There's z on the left, there's x, the data value question, there's the mean, and there's the standard deviation. So we have to carefully navigate through all of that stuff. And with that in mind, let's grab these 2 values as well, just so we don't have to keep scrolling up and down. Let's do it just once. Okay, so I think we have everything all set. Now to solve for x, just remind yourself that They told us what Z was. So that's one of the four things down. We know what X bar is, so that's two of the four down, and we know S. So if I have an equation with four variables, but three knowns, we can solve for the unknown X, the missing data value. All we're going to do, now it feels like really kind of being in a math class, is do a bunch of substitutions. First substitution is Z on the left right here. We look it up and it's a 2.18. So that value's done. On the right-hand side, I have no clue what X is, so we're just going to keep copying that in until we solve for it. But we do know what X bar is. We looked that up. It was 885.33. Lastly, go to the same formula. The denominator is S, so throw 69.68 down below. Finally, that's everything there. We still need to solve for X, but at least we have an equation at this stage. Any questions, folks, before we go to solve it? Okay, these equations are really kind of fast. I want to show you two ways of doing it. One way, I'm going to go through the algebraic steps meticulously just to show what the procedure is. And a second way, I'll show you what I would do in a calculator if you just feel really confident that you're not worried about the equation solving part. Let's start with a calculator. For those confident, if you did this on your quiz, I'm okay with that. Show me this first so that if we make a mistake, you are still going to get partial credit. But this is what I would actually calculate. Once I get all of my windows in a row, there we go. I would take the 2.18, let's type that in. And I'm going to immediately multiply it by the 69.68. Visually, I'm doing a cross product. That number in green is coming over here and multiplying, clearing the denominator. Now, if the denominator is gone, the last thing I have to do is add 885.33 to both sides. We're adding because of the negative sign. So plus 885.33. And this is the output you would get. Again, it's not recommended unless you feel like you've done solving these kinds of equations dozens and dozens of times, and you're not too worried about making a tiny mistake. You would get 1037. We're doing one decimal place, so 1037.2 hours. That doesn't quite fit. I'll put the unit in just a slightly more careful way. 1037.2 hours. So we've got it, folks. That's a solution. Again, the pattern was 69.68 multiplies, and then we just add the 885. It's tricky because we just jammed everything into the calculator. In a math class, usually that's forbidden. We want to show our steps. But if I know what's going into your calculator, even if this value is wrong, you would still get a lot of partial credit. I would assume you just made a small miskey in the calculator. But web site is less forgiving. So let's do this a second way, just taking the meticulous step-by-step algebraic work here. First, any questions at the moment? Okay, so if I was going to work this out carefully, here's what I would do. In any equation that you're solving, you almost always want to eliminate the denominator. It's hard for me to even think of a case where you wouldn't want to. So I'm going to immediately multiply the right-hand side by 69.68 and the left side, 69.68. It causes a cancellation going this way. Then we would have to pull up the calculator to evaluate the left-hand side. But on paper, this is what it looks like first. I would take 69.68 times 2.18. So we're up to 151.90. If we're rounding to one decimal place, I'll keep 3 places just to be extra accurate. That's probably overkill, but it definitely can help. So 151.902. So that clears the left-hand side, or gives us the left-hand side, clears the denominator on the right-hand side, where it's just x minus 885.33. Really, it's the same kind of thing we did in the calculator. In the calculator, we did multiply those two numbers, And then we added 885.33. So we're really kind of just doing the same sort of steps. Does it make sense to folks to that stage there? Okay, last thing to do, we'll go plus 885.33 plus 885.33. This bar here just says tally both sides of the equation. So the left is just going to be X. And on the right-hand side, we're going to go plus 885.33. Finally, we get the same result, 1037.2 in hours. Well, we did it, folks. And again, we did it two ways just to emphasize, if you like doing that step-by-step algebra, that's a good way to go. It's probably preferred in all honesty, but I am okay with just jamming it to the calculator. We'll be doing that quite a lot in some problems regardless. Well, sorry for running over about a minute. Any last questions, folks, before we call it a night? Okay, have a good one, everyone. And when we come back, if there are some burning questions you'd like to discuss for a review, please definitely plan on bringing them. I'll be happy to try to address those.